Welcome to educator.com. We've got another lesson for Introduction to C++. Today we're covering arrays and pointers. Okay, now arrays use a chunk of memory. I don't know how you want to call that, a block of memory, a pizzazz of memory, but there's a lot of memory will be in a chunk, and then you can access pieces of it through the array. You declare it with square brackets. That's where you will see square brackets as an expression in size, which will give you how large you want, how much space you want for that array. And specific elements within an array are also use the square brackets, but then there's an index into the array to get, you want the 0th one at the first, you want the first, second, third, you want the last one. That would be your index inside the square brackets. And they can be multi-dimensional. You can have your grid where you've got 2 square brackets, which indicates a 2-dimensional array. Or you can have a 3-dimensional array, you put 3 sets of square brackets in there, as many as you need. You can initialize them at compile time or at runtime. Now, one of the things about it, we looked at this a little bit, you have character strings. This is left over from C, where you have an array of characters can be considered a string. Now in C++, the preferred usage is to use the string object, but there are occasions when you will want to use the old-fashioned C version, the character string. We'll have a brief discussion of that. Now in pointers are similar to arrays, or at least in the way you access the data in an array. You can either use your square brackets, or you can use a pointer, which holds the location or the address where the data is located. And there's a bunch of different ways of using pointers in C++, but the arrays is why they're combined in this one lesson. It's most useful when you're dealing with arrays. And we will deal with the reference and dereference operators. We'll talk about pointer arithmetic. Arrays can be used as a function parameter, but there's no call by value for an array. Think about it, arrays can be huge. The way copy by value works, it takes a copy of the parameter in the function, and it uses that copy. Now, if you've got 12 gazillion array, and you're going to copy, that takes too long to copy 12 gazillion, so we don't do that. Then we have the new and delete operators for allocating and deallocating memory. If you've had any familiarity with C, you might be aware of the malloc function, which allocates memory, and the free function, but we won't be using those because there is an actual operator in C++ to do that job. Okay, up until this lesson, we've been dealing with a variable that has one memory location. You can have int a, and it's equal to 7. And so the compiler would say, oh, okay, let's put a little chunk right here, and we're going to call that A, and we'll put a 7 in there. A single piece of data. Now with arrays, we're not limited to one. Now we can have as many as memory as we can hold, and in some cases even more than what your memory can hold, but we won't cover those types of issues. So now we can have an array, and using those square brackets like we mentioned earlier, and say we've got 10 slots. So now the memory, if we look at it as a box with boxes in it, and I'm not going to try to get exactly 10 here. So now this is your array variable, which has got 10 slots. So there are multiple pieces. The pieces of data tend to be the same type. There's ways of getting around that, but we won't talk about those today. The compiler allocates enough memory based on the size and the number of elements. So an int array is larger than a char array, but it's smaller than a double array. So the double, each one of these slots to put a number in has got to be 8 bytes across. Whereas for the integer, it only needs to be 4 bytes across. And the compiler takes care of all that for you. So you don't have to worry about where things are and that sort of stuff. So here we have int, which are 4 bytes. We want 100 slots for Fred. 100 times 4 is 400 bytes. Here's a short. Barney is shorter than Fred, if you're familiar with the cartoons. That's only 2 bytes. With 2 bytes, but we've allocated 200 slots. So 200 times 2 is 400 bytes. Now here we have a char for Pebbles, 400 characters. A char is 1 byte, so we've allocated 400 bytes. And we'll also look at the multidimensional arrays, where you've got an array of arrays. So here we have a 3-dimensional array, Mr. Slate. This is a double. It's 2 by 5 by 5. There's part of your homework assignment is to calculate how many bytes this is going to take. Using the size of operator, which works, will also give you the correct answer, but see if you can work it out before you try that. And you should try that also. Okay, how do we declare an array? We declare an array pretty much like we declare any other variable, but we add those square brackets to tell it how much space do we need. It's possible to calculate this on the fly. Sometimes it's a good idea, sometimes it's not. Your best bet is to have something that you're going to use as a variable. Now, we haven't talked about this before, but we have the const keyword that says this value is not going to be changed in the code. This is a constant. Now, we can use max values instead of 500. So here we have the value is declared to have max values of numbers of slots, which will be 500 slots. And then we want to do some calculations for each value inside this array. So our loop is from 0, which is the first slot until we're less than the max slot, because the actual max slot, which we'll talk about some more, goes past. And then I plus plus. So this will go from 0 to max values minus 1 and do our calculations for values of I. Now, if you, during the course of programming, or someone adds features or finds bugs, you need to change this value, you need to be 600. Okay, fine, we change this constant to 600. You don't have to go searching for all the 500s all throughout the code and then worry about, well, is this the correct 500? You might have several things that want to be 500. You don't want to change the wrong 500, but if you have max value, you could have something else. MV is equal to 500. It's totally unrelated to max values. So you can't just go globally change 500 to 600. You'll cause problems. So if you just change max values automatically become 600 throughout the rest of the code. You recompile everything, you have less chance for errors. Okay, how do we get a particular element out of the array so that we can do some work on it? Well, we have those square brackets again. This is not a declaration, this is an expression. So here we have int w is equal to Wilma of 27. This gives us the 28th element. Now remember, this is C, this is C++. This is computer code. We start from 0. So 0 is your first element. 1 is your second element. 2 is your third, etc., etc. Here I have an array of 3. I've allocated 3 slots here. But if you go to the third one, that hasn't been allocated. Or not the third one. If you go to the fourth one by using index 3, now you're in trouble. So the last element is the declared size minus 1. I can't stress this enough because there are more mistakes in code because people forget this minor detail, or they gloss over it, or they ignore it, and all kinds of problems can happen because people are not used to thinking this way. So get used to thinking this way. The compiler for C++ will not catch range errors. There are other compilers in other languages that will catch these at runtime. C++ is not one of them. So here we have an example. We've allocated 4 slots for A. We're going to put 100 into 0. We're going to put 90 into 1. We're going to put 80 into 2. 70 into 3, 50 into 4. Yep, no, you can't do that. It's an error. We've allocated 4 slots. You try to get to the 5th slot. The program will corrupt other data or cause something else to go wrong. You might even cause it to crash. Because obviously what the compiler has to do is it's allocating memory. It says, okay, we've got A. We're going to put A here. We have some other stuff. We'll put B there. And so you've got 4 slots for A, and then B is starting someplace else and coming over here. The compiler doesn't catch that error. You end up writing some other error, some other area. It may not be a variable. I tried playing around with this. And I declared 2 integer arrays next to each other. And I tried to see if I could get it to overwrite from one to the other. And what I put like a 10 here, and I had 100 there. And I said, let me access A of 5 and see if I get this 10. I didn't get 10. I got a 1. Well, why did I get a 1? Well, it turns out I had a literal 1 someplace in the code, like something equals this plus 1. And the compiler decided to put the constant literal 1 after my array, which is what I was accessing instead of the array. And if I were to change that, definitely cause problems. So be very careful of that. This is sometimes known as the OB1 error, off by 1. Okay, let's get into a multi-dimensional array. We get that chunk of memory, we can split it into as many dimensions as we need. We designate it by adding more square brackets. So we can have a grid which has got 10 on one side and 20 on the other side. And that's your 2-dimensional array. You need to be 3-dimensional. Let's put another grid on there. So here's Betty, which is 3 by 5. You should think of it as an array of arrays, because if you do it right, each array does not have to be the same length. We're not going to worry about that. The way we're going to work it, each array will be the same length. It'll be just like a grid. We have, this one is 5 by 3 by 2. So we've got a grid that is 3-dimensional, which gets to be very difficult to draw. And if you think this is hard to draw, wait till you have another dimension added, then we get in hyperspace. So this is 5 arrays. Each of those arrays has got 3 arrays, and each of those arrays has 2 elements. Here we have a character array. What we have here are 50 names. Each name can have up to 30 characters. As a string, as a null terminated string, where the last character has to be the null terminator, and you get a string up to 29 characters plus the null terminator. Now it's easier to initialize many things at compile time. So what the compiler will do is it will load up, as it's loading up the code, it says here's the code for A equals A plus 1, here's the code for this, here's the code for that. It will put the data in memory at the same time. That saves you time. So if you can compile things and if you can initialize things at compile time, that's better. Because that saves you the execution time of having to go run it and set this equals that, set this equals that, set this equals that, set this equals that. Because That's tiresome not only for the computer doesn't get tired, but it's certainly tiresome for me as a programmer, as you as a programmer, to have to type this over and over again, or to read it in your code over and over again. So here's an example. We put the curly braces at the beginning and the end of what we want to initialize. So here we have a float. It's called quintile. We define 5 slots for it. We put it inside the curly braces. It will put 0.2 in the first one, in the 0th element, 0.4 in the second, and then blah, blah. So if you take a look at that in memory, where we've got our 5 slots, we've got 0.2, 0.4. You can do the rest of these on your own. And this is where they're all going to go. This will be at compile time. Your compiler, when your program starts, this will already be set up. You can leave the size out in many cases. Just leave your brackets empty. And then put your initialization. The compiler will count them for you. It's 1, 2, 3, 4, 5, 6. So remembering the off by 1 issue, 6s of 5 is 60,000. This is 0, 1, 2, 3, 4, 5. Now, next question, how do you initialize what is a multi-dimensional array? You nest your curly braces. So here's your outer curly braces for the entire grid. This is a 4 by 5. So we've got, this is 4 arrays of 5 each. So here's your first array, second, third, fourth. Remembering again, this is 0, 1, 2, 3. And then the nested braces to initialize this array where it's 0, 1, 2, 3, 4. Now, there are occasions you can leave these out, or you can leave this one, you can leave the first one out. The first one is considered the major axis. So the compiler will count them for you. 1, 2, 3, 4. It will put a 4 in here for you. Later on, so this is something to keep in mind how you organize your data, because later on you go, well, we need one more BB for this. You don't have to change this. You just insert your curly brace for 1, 2, 3, 4, 5. And don't forget the comma. So now we have 5 arrays of arrays in BB. Again, the compiler will keep track of all that, but it will check this. If you put too many, it will complain. If you put too few, it will just leave them blank. You'll either leave them, it depends on the compiler whether it will actually initialize it to 0 or leave it to whatever was there before. It's best not to rely on that. Better just make sure you put whatever value you want to be there. Okay, now we have this special nature of a character array. A character array is just like any other array, except it can also be a character string. So therefore, there is a special way to initialize it. So here we have, not specifying how many Western states there are, but we're going to say each Western state has no more than 30 characters. Now with that null terminator, that's no more than 29 characters. So we have Washington, Oregon, California, blah, blah, blah. So this will create an array. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This will be a grid that's 11 long and 30 across. And we'll begin with Washington on the first one. The second one will be Oregon, etc. You can't do this with any other type. Just the char type will let you do something like this. Now, since this is C++, and we're trying to discourage the use of the C-style character string, we use our string object, which works similar, or at least your initialization is done exactly the same way. But now instead of a grid, this is no longer a 2-dimensional array. This is a 1-dimensional array of string objects. And that's why there's one set of square brackets here. Now this leads us into pointers. A pointer is a very, very, very powerful, very dangerous, very valuable part of the language. It's probably the one thing that'll get people into more trouble, create more bugs, because it is so powerful. So it's one thing to use very carefully. When there's a different way to solve a problem, it's maybe better to use the other way. But once you get comfortable with pointers, once you get used to using pointers, you'll find a lot of cases where pointers are the best way to handle a problem. So what it does, it doesn't store the data itself. It does store data, but what that data is the address where you can find the data. Going back to this other example, we have int a equals 7. So somewhere, if you think of memory as a big, huge, long chunk of bytes, somewhere is an address where a is going to be stored, and the compiler will put a 7 there. Now you have a pointer b will be equal to the address of a. Somewhere in this long bit of memory will be a b, but it won't have 7. What it will have is the address or a pointer to where a is located. So here we have operators for pointers. We have the reference, that's the ampersand, where we get the address of the variable. Dereference, where we take that address and dereference it to the actual data. New will go out into memory and grab a chunk of memory out of the heap and apply it to a pointer. Delete will take that memory and put it back into the heap. So here's our pointer declaration. We put the asterisk, that makes this a pointer to int. Here's a double, that makes it a pointer to double. Now this type is very important because then the compiler knows how large that data being pointed to is. So it needs to know that when, in this example here, the integer pointer b pointing to the address of A, it needs to know that this data being pointed to is 4 bytes in length. So the reference operator gets the pointer. Here's an example just like what I did here. Albert is equal to 900. Somewhere in this long chunk of memory, we have Albert. And we put a 900 into it. Now this pointer to Albert gets the address of Albert. So it might be next to it, it might be up here. Let's put it down here because there's room. So P to Albert, now has a pointer to where Albert is. Now, if you count this from 0 and blah, 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 this turns out to be address number 4000, what have you. You'll put a 4000 in there. You know, it's not likely to be 4000. It could be almost anything because it depends on where the compiler decides to put it in memory. Most of the time, you're not going to worry about exactly where it places it. You can print this out. You can say print P Albert. And it will print the address where Albert is keeping data. But most of the time, that doesn't do you any good. You will want to dereference to get where it will tell this, go to this location and get the actual data. So P Albert does not store the value 900. It stores the address where Albert is storing 900. So we're going to reference data, we're going to dereference data. When we get the data stored at the location pointed to by a pointer, it's called dereferencing. The pointer can be used just like any other variable. It's just an extra step for the compiler. So we have integer bud 500, and we have a pointer to bud is bud's address. If we print this out, this will print 500 because this is dereferencing. See, pbud is pointing to where bud is. So this is saying, go to where pbud is pointing and grab that data and then print it out. So this will print 500. We can increment that. So go to that address where bud is pointing to, where there's bud, grab that data, which is 500, add 1 to it, and so we will actually go to the memory. It will ignore bud. Bud is here. The 500 there. We've got pbud, which is pointing to where bud is. And we're saying, go to where bud is, which is here, take that value, add 1 to it. So this makes this 501. So when we print out bud, bud hasn't changed the actual address of bud. The variable bud is still pointing to the same location. So when we print out bud, it will print 501 because the pointer to bud changed the value of bud. It's kind of like giving your car keys to your neighbor. He can drive your car now. Now, be very careful with pointer arithmetic. You notice I put parentheses around here to tell it definitely dereference this first. Because if you do this, it will increment this first. So that means the address pointing to bud will be incremented, which will now point to the variable after bud. And then increment that. You have no idea what that'll do. Like I said, there could be more memory, another array there. There could be constants stored there. It could be all sorts. This can cause all kinds of havoc. So it's totally impossible to predict where the compiler is going to move that to. So be extremely careful with pointer arithmetic. Most of the time, it's not safe, especially that example that we just did now, a second ago. But if it's in an array, then it's safer. The pointer and array can be interchangeable. You can have an array and reference into 17, or you can say array plus 17 points to the same location. You might put that inside parentheses so that you can increment it. These two are equivalent. So here we have an array. We've got 1, 2, 3, 4, 5 things in there. We have a pointer. There's no dereference. We don't need to get the address because the compiler knows that this is an address containing more than one thing. So we have this as pointing to that. If we point out, if we dereference this, that's okay. Let's draw this out here. There's 5 of them, right? This is array. This is where array is stored in memory. Of course, there's more memory up here, which we're not going to look at. There's more memory down here, we're not going to look at. Let's put a little larger barrier there. So now we have a pointer to array, which now points, let's say that's PA is here. It points to where the array is located. So when we dereference it, we'll get 100. If we increment that slot, we'll make this 101. So here, array 1 is 201. I may have made a mistake here. Oh no, I see what I forgot a cut statement here. We incremented PA, we added 1, we have the pointer to the array, which is defined on this line right here. We printed it out, that prints out the 100, and then we advanced the array without dereferencing it. So that takes this, which is pointing here, add 1 to it. We're just adding 1, so now it points to the next slot in the array. And the reason why this is safe is because we already have allocated a chunk of memory that's going to be contiguous in memory. So when we add 1 to it, we're going to the next slot. So now when we dereference it, we'll print 200 because we had put 200 here. So now we're dereferencing to 200, adding 1 to it. That makes this 201. Make that back to 100. Now if we print out array of 1, which has not changed, it will go to that value and print 201. And we can also dereference array this way, which will print this one. And as I had mentioned earlier, you can say array plus 1 and dereference it, and that will give you the second slot. Or you can do plus 2, that'll give you the third slot. So arrays and pointers, you can use them back and forth. It's better to keep in mind what you're using the data for and then stay consistent with that. Now, this is a function call by reference. Before we had the class, we learned about functions that does call by value, where the function will actually make a copy of the parameter. You can't do that with an array. Copy by value involves copying the parameter. An array can be very huge, therefore it's always passed by reference. What it passes into the function is the address of the first element of the array. And this is where your interchangeability between arrays and pointers can be most useful. Now, unfortunately, there's no automatic way to determine the size of an array. So your best bet is to have another parameter or some other mechanism that tells you how large is the array. Now, with character strings, as we've seen, the last character will be 0. And that's the way it's done with character arrays, traditionally. You don't have to use that. You can also have another variable someplace that says this is how long this is. But you need to know how long that is when you call the function. Otherwise, you get all kinds of heartburn. So here's an example. We have 2 ways of getting an array element from within a function. This is where we're using the pointer. So we can call my function. I can have someplace I have int a of 12, and I can just call my function. And I say, well, it's 12 long, and send it a. And this will get passed in, and we'll look at it as a pointer. Oh, excuse me, this is not an int, this is a float. And the erasure works. Excellent. And so this process will do, the loop will go from 0 to 1 less than the size, and increment the index, and then print out that value. So whatever's in here, I've got 12, we'll just print 1, 2, whatever these values are, we'll get printed out, and then advance the pointer to the next slot in the array. Now, that's an okay way of doing it. The compiler will let you do it that way. But if you're dealing with an array, if the array is your best description of the data, leave it as an array. Use it as an array. That makes it less confusing. The compiler will use either of these ways interchangeably. But humans think a certain way. So this way is much easier for people. Now, there are occasions when you do need a pointer because the way the data is organized, the pointer is the best way to look at it. But in that case, use a pointer. But in the cases where the array is a better way to organize the data, stick to using the array. Now, as I mentioned, your character string, you have char f and is equal to hello. It will store that byte by byte, H, E, L, L, O, and then the 0 null terminator. So the compiler, the execution runtime knows when it hits that, oh, that's the end of the string. So it's null 0. If you put it in a character string, and we've had the class on how to do that, you quote it this way. So here's an example taking advantage of that. So we're setting it an array. So we have char f, and then we're going to call, I'm not going to type it all out, print each character, and we're passing it in f. I don't have to send it a size. It will find out the size when it gets to that null character. So the null character, this expression will evaluate to false because it will dereference it, find out what's there, and if what's there is 0, 0 is considered false. So while it brings up data that is not false, it will continue to advance the pointer. The ch begins starting at h. After we print out h, we'll go through and we'll add 1 to it, which points it to e. So here we have print each char. These are my chars. You'll print out t, h, e, blah, 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 r, s. And when it gets to 0, it'll jump out of the loop, exit, and that'll be the end of it. Now we can allocate memory for arrays using the new operator. Memory is taken from heap. Every program that runs gets a heap of memory that it can use for allocating space. if what is given is not large enough, the program behind the scenes will ask the operating system, says, hey, I need more memory. Can you give me some more memory? And the operating system will either say, yay, here you go, or nay, I've run out, or whatever happens. And you get run into virtual memory issues where the operating system will say, well, this is taking up too much memory. This program is not being used right now. Let's save it off the disk. And we'll go off the disk, get something else, and run that. That's how operating systems do multitasking. When it gets finished, okay, we'll put this back on disk. We'll go back, get this guy, put him in, and run this again. This is not a class about operating systems. We don't deal with that. Just to know you've got a heap of memory, and all you have to worry about is there's some memory out there. And when you need memory at runtime, you can make the request for new, give me some memory. So here we have an example. We have a pointer to an array. We want a new integer with 5,000 integers. So the compiler calculates, well, 5,000 multiplied by 4 bytes per inch. I need 20,000 bytes. Let's go to the heap, get 20,000 bytes of memory, and our array will now point wherever in memory that may happen to be. You have no idea where that could be. You don't worry about where that is, as long as you get an actual value here. So now we can go through and actually do some arithmetic on that array that we just got from the computer. The point I wanted to make here is be sure you match your new with a delete, because as your application gets bigger and bigger, you'll find more and more cases where you need to allocate some memory, and you need, when you get through with it, delete it, give it back. That'll put it back into the heap again. The operating system concerns itself with organizing that and moving things around as necessary so that you can always ask for a continuous piece of memory. But if you neglect to do this, or if you do that at the wrong time, you can cause problems in your code. Notice the syntax for an array. I'm deleting this array using the square brackets. Now, the way I like to think of it is like open and close parentheses. We've got new, that opens our parentheses. We work on it, and then we've got delete is our close parentheses. And like parentheses need to match, your new and delete need to match. So we can have a new for something up here, we have new for something else, then delete this and put that back on the heap, and then delete that and put that back on the heap. Something very, very careful. If you don't delete memory, you'll have what's known as a memory leak. Especially like if you're in a loop. It says, I need new memory. You're in a loop. I need new memory. I'm in a loop. And if the loop goes on too long, you'll allocate too much memory, then your system can crash. All sorts of bad things can happen. But if you're in the loop, I need some memory. Okay, work on it. Give it back. You're back in the loop. Go back. Give me some memory. Do some work with it. Give it back. So new, delete. New, delete. Always keep them paired up. And here we have a famous array of pointers. You can put a pointer in your array, where each array is pointing to a pointer. Anyhow, that's the end of today's class. Thank you for viewing it, and I'll see you next time at educator.com.